What's going on YouTube? Josh here, and that was awkward. Let me just give you a heads up that this video is highly technical. It is about Rholang, which is kind of reflective higher order calculus, and I know that's what you guys come to this channel to watch, is some calculus and reflective higher order calculus stuff. If you want to be at the forefront of blockchain technology, watch this video. It's a smart contract language that will be used on the blockchain for RChain. There's a lot of chains there, but if you go to CoinMarketCap and you look in the top 50, you'll see RChain there. Right now it's just a utility token, and those will be converted to revs once the actual blockchain launches sometime, hopefully in December. Now the reason that I do this is because I may have mentioned in a previous video that I host a meetup about cryptocurrencies and stuff like that. So I host one for a company called Pyrofex, and right now they're the company that's writing the smart contract language for RChain. So they're kind of like two separate entities. What's the benefit of RChain over other tokens right now? Well, so they're aiming to kind of fix some problems that let's use Ethereum. So right now you have two contracts that run at the same time on Ethereum. Which one does it run first? Does it run this one or does it run this one? So it has to pick one and then rerun the other one if they both come through at like the same time. Like I don't know, they try to run at the same time. I'm explaining this to the best of my knowledge, so I'll put a little asterisk here. I mean, I have any idea what I'm talking about, but I think I do, at least a little bit. Anyway, so the benefit of Rholang is that if you have two smart contracts that run at the same time, it checks to make sure, is like, okay, is there anything in this smart contract that would activate this smart contract? Okay, no? All right, then merge them together and we'll just run it all at the same time. So that's kind of how smart contracts run. So you have a key here, and then you have another key here, and if they meet that smart contract, how many times can I say it? Breathe. All right, that's a lot of mumbo jumbo here. So the way smart contracts work are you have a key here and you have a key here. Once this key meets this key, it says they shake hands and that contract runs, and there's nothing you can do to stop it. And so that's why it's kind of it's not scalable. Ethereum's not scalable if you can only do this one and then this one and then this one and this one. If you have a bunch of requests all coming in at the same time, thousands of transactions going on like per second, then then the transaction time takes forever because you got to wait for your turn for the smart contract to run. Okay, this video is presented by a guy named Kyle Butt, and he's an engineer there, and he'll be talking about the syntax and how it works. Don't worry if you don't understand the syntax. I'll actually link the PowerPoint that he's using in the description below. There's another link I'll put in the description below so that you can go see a demo of RChain and kind of just walk through what a smart contract would look like, and then you can kind of like figure out what the syntax looks like. It has a lot of keywords from different languages and some syntax from different languages, but you're just gonna have to learn it or just keep following through. You stick around, watch the video. It's long, you can skip through it, come back to it later, try to understand it, but I'll leave all the resources that I think that you'll need in the description below. If you have any questions, you can go to the RChain co-op, or I have a Discord. Be sure to hop in the Discord, the link for the Discord. I keep doing this, but that means the description. In the description, there's a link for my Discord, and you can just go there and click it and join and ask me any questions. I'm always there, I'm always hanging out. We'd be happy to have you. If you want to see more videos like this, you're interested in the series, be sure to hit that little subscribe button, click the bell so you get notifications when I upload a new video. Let me know what you guys think. You guys want to see a Pyrofex series, like a day in the life of a blockchain developer, like this is Pyrofex, this is what the forefront of blockchain looks like, etc., etc. I have a whole bunch of ideas, and I really think it'd be interesting for people that are interested in cryptocurrency and programming to do. And so with that said, finally, go ahead and enjoy the video. Okay, so I forgot one thing, and I filmed that like 10 times, but I just want to mention that they are hiring. You can work remote or in Utah, so be sure to check them out. I'll leave the link to the actual company, Pyrofex, in the description as well. Okay, enjoy the video.
What works as of now. Okay, so some background. Rholang is an implementation of the row calculus, just like you might call Haskell or ML an implementation of the lambda calculus, and it's got additional features to make it better for end-user programming. So the row calculus the row is actually an acronym. It stands for reflective higher order pi calculus. And those are kinds of mathematical models of parallel programming that have been around for a long time. And so one of the insights that led to row calculus was that most of the pi calculus presentations just assume that there's some set of names. And in row calculus, Greg Meredith, who created the row calculus paper, he wanted to add structure to names. And so he realized he could just reuse the structure of processes to get a structure on names. And as we go along, you'll see why this is significant. So in order to get anything done in Rholang, all computation really happens because of either a send or a receive. So sends go to a single destination. We call the destination of a send a name. You can think of it as like the name on an envelope, or the name gives you an address where you can meet with people that are expecting the data you're sending. You can actually use the names as a key value store, and at the end maybe I can show you that. So that's send, and then for every send, unless you're just like, the golden record on Voyager, you need a receiver. So receive in Rholang can have multiple sources. So there's this asymmetry. Sends are singular, receives can be many, at least one. And this allows you to do things like take atomic locks. And you can do it, or to only fire a piece of code when data is available from two different sources. And here's a quick example of what some sends and receives look like. So here we have a send to a channel named standard out. And in fact, if you write to the quoted string standard out in the existing Rholang interpreter, it will actually print things out and have an effect. And then this doesn't work yet, but you could fake it by adding a send to standard inline. But this line, if standard inline were a special channel with something listening on it, this would read in a line from standard in and write, and then write that line to standard out. All right. Like I said, all of the computation in Rholang occurs because of sends and receives, and they're on sends and receives require names either to send on or to listen on, and they need to know the names need to be the same in order for something to happen. So in Rholang, all names are quoted processes, and the way that you write quote is you use the @ character, and you've already seen this used on the previous slide. So standard out is a process, @ standard out is a name, so the quotes around it. The string is a process, and so quoting it gives us a name, and where we can produce a send on the process quoted string standard out. So names are quoted processes. So given a name, we might want to actually use the process that's quoted as a process. So we can use the star to dereference it. And if you look, I was sneaky and I stuck that into the example. So X here is bound to a name, and then over there we use X as a process to send the value on standard out. So a send takes a name, and that name is this part right here, and a list of processes. And that's this list right here. So if we go back to this slide, that's a quoted string, so it's a list of size 1. And I believe that sending lists of size 0 actually works at the moment, but I'd have to go check. So here's a send. We're going to quote this process, 7 plus 8, and we're going to send the values 9 and 10 plus 11. But top level expressions in general don't get evaluated. But here, when we quote this expression, we do actually evaluate what's inside, and the time when it's evaluated is on the actual send. We leave it alone until the send actually, it turns out we're actually going to evaluate this send right now. So first we need to evaluate any top level expressions in the quoted process. And we also evaluate any expressions, any top-level expressions in the quoted processes that we're sending. So if you evaluate these two things in parallel, so here's a send on 7 plus 8, and we're sending the values 9 and 10 plus 11. And if we were to listen on channel 15 for the evening news, just kidding. And so we get these two values and we send them bundled as a list to standard out. And this is the actual output. I checked it while I was working on these slides this afternoon. So it actually prints out the list 9 and 21. This is just an artifact of, it should just print the list 9, 21. So that's some more detail about sends, receives. Similarly, if there were an expression in the channel you were listening on, so like this is listening on 15. If this were listening on 9 plus 6, this would also work because we would reduce this channel when we would evaluate the expressions inside of there before we tried to do the actual listening. All right. So receives can be from more than one channel. So here we have one send or one receive listening on two channels, the quoted string A and the quoted string B. And here we have a send on A of 74 in parallel with a send on B of 75. And so executing this will print 74, 75. It's a great song. Nobody knows it anymore. All right, so the receives are a little bit more complicated than sends, so there's some more information. Oh yeah, that's because of patterns. So in general, it's been looking like, well, we can get a variable from a receive and we send a single thing. And here we can get multiple variables. And the number of things that you send has to match. But in fact, it's a lot more, it's a lot more powerful than that. We'll expand on how powerful it is as we go through. But the simplest kind of pattern that I flipped back is just arity matching. So this send sends two values, and this receive is expecting two values. And if this receive were expecting three values, or this send only sent one, they would not match. So both things would be running in parallel, but neither would neither would trigger the other. So what happens is when there's a send and a matching receive, the send disappears and the body of the receive executes. And if they don't match, they both just stick around waiting for a send or a receive, respectively, that does match. Okay, so we can talk more about what the patterns are and why they're powerful. So the patterns are structural types for names, and the way that you produce a structural type for a name is to quote a structural type for a process. It kind of works out nicely. There's a nice symmetry between the type of a name and the type of a process. You know, it comes from, you quote a process to get a name, and you quote a type of a process to get the type of a name. If we have time and interest, I can go over what you can do with matching, but we may only just scratch the surface. And I'm going to sneak in some syntax that I haven't shown you yet, but this is an example from, or a snippet from one of the examples that we ship with the distribution. So this, we can read most of this, except for this bit right here already. So this is a pattern, so here's a pattern. There are two patterns. This read right here is expecting exactly the process, the quoted string get. Exactly that. So anything else in that first position will fail to match. And it's expecting an arbitrary name, ret. So ret is a free variable, and even if it were bound, it's considered free here because this is with shadow. So this matches anything, and this matches exactly one name, get. And we're reading from method, and you can assume that method is bound somewhere outside. And then over there, so we've quoted the structural type val. So val is the type, or val is a binder, but it also matches an arbitrary process. But the nice thing is that inside the body, ret is treated as a name, and val, because we put the at in front of it and quoted a process pattern, is treated as a process. So and maybe later I can pull up the context where this came from. But basically, we have some channel state. We're going to read the value from state whenever we get, whenever someone sends on the method channel the string get and a return channel, and we're going to write whatever was on the state channel to that return channel, and we're also going to put the state back because we like to clean up after ourselves. So down here, so that's one thing you can do. You can simulate method calls, and you can specify. This actually kind of acts like a lock. It sequences read. If someone were trying to modify the state, they would have to take the value, modify it, and then put it back. And so this is an explicit synchronization between readers and writers. So here's another example. So this we can quote a list here, and why wouldn't you just use arity matching? Well, there's reasons. One reason you might is that you can use these same patterns in our spatial matcher, and we'll get to that in a minute. But this right here would bind X and Y, provided that whatever was sent on A was a list beginning with 7. So if we were to send 7, 8, 9, and then we were to print it out, can anybody guess? So if we were to execute, these are separate segments. If we were to execute just this segment, can anybody tell me what would be printed on standard out? Yeah, it's the list 8, 9. So that's what would get captured. Yeah, it's printing X, Y. If we were to print 7, X, Y, then it would print 7, 8, 9. So one of the other things that you can do is you can do a remainder pattern. So you can say, I want this method to fire if I get n or more items. So like a good example of this would be, this feels a lot like printf in C, where it's required to pass a string and then a variable number of arguments afterward. So you can specify a remainder pattern. Unlike the other patterns in the slots, you can't specify a more complicated remainder pattern. Because if you knew what the remainder was going to look like, you could have pulled that off and made that part of the pattern. So you're not really if you know what the remainder looks like, you're not really losing any functionality by us saying, no. Your remainder you can only just quote a var. You can also do ... at underscore, which is a wildcard, and we'll just throw away the remainder. So underscore is like a variable, but it doesn't bind. There's some subtleties in the matcher, but I can get that at the end. For now, underscore just acts like a variable, but it doesn't act like a binder. So then variable is bound to a list, which is those the square brackets that we saw earlier. The list could possibly be empty. And it's at whatever's sent above the things already supplied. So if we execute this example where we send on A, yes, no, I don't know, and we can say for remainder x from A, print out the x, and then you'll see that it's been turned into a list. Yes, no, I don't know. When we decide that the patterns in the receive match the data in the send, the data in the send is considered consumed and it goes away from where we're tracking what's available. Any binders in the pattern are made available within the body. So it's kind of, you think of it like a function call or a let statement even. So RChain is, we're working on a programmable blockchain like Ethereum. But instead of Solidity, we'll be deploying things in this language called Rholang. So there's a couple things that we need to talk about when you have sends and receives together. One of them is you can have competing sends and receives. And maybe we should talk about this pipe here, and I realized I didn't do that. So this pipe means these things are running in parallel. So we have a send on A running in parallel with a send on A, running in parallel with a receive, along with one receive on the channel A. So if we were to execute this, it will either print 18 or 19. And unfortunately, I think it will just pick one of them. It shouldn't, but it does. I gotta figure out why. And a similar, we call this a race. A similar thing would happen if there were one send and two receives. You can get, a K by L race where you have K writes and L reads. There are a bunch of what they call process calculi that are models for parallel processing. And they use these kind of communication models. And this one's based off of a particular one called, like I said, called row calculus. Some things that make it easier to use. The row calculus is very much a model and not intended for like, oh, I was gonna go write something in this. All right, so there's some send and receive asymmetry. So if you're paying close attention, you might have noticed that we were sending processes and receiving names. So that's an intentional asymmetry. And the goal was we figured people would use names and processes about equally. And we didn't want to privilege one over the other in terms of like sending it and receiving it. And so it's actually, it seems weird, why would you do that? But like once you kind of get used to reading it, it kind of feels nice that like, oh, well, when I receive, I know exactly what I'm getting. And when, yeah, it balances out. It actually feels nice. Most of the time, if you, like if you're sending on a name, you'll see a star. And if you're receiving a process, you'll see an @ in the pattern. And there's kind of a balance there. And I kind of like the balance. I think it's aesthetically pleasing. Semantically, we could have done it, like you always send and receive names, and so like it's not like it's just an aesthetic choice. It doesn't really change the way Rholang works. It just changes the way that Rholang looks on the page. All right, so it's a nice overview of send and receive. So now we're going to talk about some of the other things that Rholang does in addition to send and receive. It'll make it, because send and receive are the engines of computation and they're like actually what makes stuff happen, it makes sense to talk about them first and then, oh, and I realized I just completely skipped out on expressions, but that's fine. So in Rholang, everything is a process. You'll notice that, like we quoted the string A. So this send 7 is a process, but so are the string A and the number 7, if you were to just try and evaluate them, they don't do anything. So like I actually have the interpreter here, and I'll blow this up so that it's moderately legible. But like you can run 7, it's a process, but it doesn't do anything. And similarly, nil is the empty process. The string A is a process.
Define variables?
At the moment, you can't, other than, I'll show you in just a minute. There wouldn't be any problem adding that to the language. It's just not something that we've done yet. All right. All right, so if they're behaviorally equivalent to the empty process. So if we take an arbitrary process P that's running at the top level, and we put it in parallel with the string A, it's going to behave like P. It's not going to change P. It's going to be true for any P. There's the processes for which that is true for all P. They're called ground processes. So we have the atomic ones. We have booleans, strings, ints, and URIs. We plan on adding byte arrays to handle cryptography. So you can produce some bit of code and turn it into a byte array and then verify a signature on it. So all of the crypto functions that we're planning on working on will work on byte arrays. And byte arrays will be ground terms. And so when we have lists and we're working on sets, maps, and tuples, they're just not completely fleshed out. But for an arbitrary process X, the list containing X is a ground term, even if X is not. So, but it's not an atomic ground process. If you take something and make a list out of it, and then you put it in parallel with P, it's not going to have any effect. Being in a list kind of negates its effect. And so expressions, almost all of the expressions, will only, if they successfully evaluate, will only evaluate to ground terms. So like addition, right, or string concatenation. And so we don't evaluate them at the top level because we know if they succeed at evaluating, they're going to produce a term which has no effect. And so we just don't bother reducing them at all because we know that, and in fact, there are a few expressions that are in the source that for instance, method calls can produce, so like on lists, we have a method called nth. So like this list.nth0 would extract X, and now that process, if X is not a ground term, could have side effects. And so there are a few things where we do actually evaluate them at top level. Okay, so moving on. One of the things that Rholang has that's definitely not in row calculus, although it could have been, is new. So new gives you unforgeable names. And what that means is that when this evaluates, it substitutes in a value for X, which you couldn't write in the syntax. And so if we were to run this snippet right here, new X and X bang unforgeable for message from X, standard out bang message. Nothing really surprising here, right? We were using the quoted string A to do a lot of this same thing earlier. But now, if you remember, I'm not going to flip all the way back, but remember that we could have races on the quoted string A. Well, we know where X is, we know that X didn't escape, it didn't get sent anywhere. So there are no races possible on X. This is always going to print unforgeable, no matter what context it's running in, because we know that nothing else can create a name that got assigned to X and race so that something else gets there. It turns out that this is an incredibly useful property for security. It allows you to do And I kind of wish Mike were here, but this allows you to follow object capability discipline and use object capability style security. And that's the kind of security that we plan on using in the RChain blockchain. All right, so matching. I mentioned before that the same kind of patterns that are available as receive patterns are available for the match instruction. All right, so we can go through this. So contract, oh, I remember, I didn't explain the contract just creates a replicated read on one channel. So a contract loop means listen on loop, and it gets pattern. So we're listening for a list, and we're going to match that list with the, so that's a variable. We're going to match it with head, and we're going to bind the remainder. So remainder syntax is available for lists as well. And then we're going to print to standard out the head, and we're going to call loop with the tail. So we're going to invoke this contract again, so it's just an actual loop. And we're going to call the loop on 1, 2, 3. Now, anyone care to guess what's going to get printed? What's interesting is the print to standard out is in parallel with the reinvocation of the loop. So it's going to print out the numbers 1, 2, 3. But the order in which they get printed is not guaranteed. And in fact, the current implementation prints them 3, 2, 1 every time. Yeah, it's a literal arrays, but each number in this, each number at the head gets a longer and longer head start. So if it were actually being non-deterministic, you'd expect that 1 would occur at the beginning more often than 3. That it's non-deterministic. All right, so what if we wanted them to print in order? All right, so it turns out we can actually make them print in order. And the way that we do that is we use, so this is a common pattern, you'll see this a lot. We're going to use a return channel, and then we're going to wait until the return channel, until something is actually printed and before we call the loop again. So this looks basically the same, except we allocated 2 names, loop and ret. And then we're going to send standard out ACK, the head of the list, and the ret name. And then we're going to listen on the ret name. And it turns out this is already implemented. There's a standard out ACK. So what it does is it prints the first value, and then after it is done printing, it sends a message on the ret. So here we listen for an arbitrary message from ret. We don't use a binary because we don't care what it is. And then we just loop on the tail. And so this will print 1, 2, 3 every time. And it's guaranteed by the semantics, even if we were actually being non-deterministic. I do think that the technologies that we have will scale. I'm not going to make any promises yet. Other people have made promises and then told me to try and meet them. I'm not going to say I'm being recorded. Yeah. Confirm or deny any of the existing claims. I'm going to say that at the moment, RChain does 0 transactions per second because it's still being built. It's just like a Ford being built. You can only go 0 miles per hour.